In this module, we will be studying about force between two current-carrying conductors. Let us consider a straight current-carrying conductor XY of infinite length. And like any current-carrying conductor, it produces a magnetic field around it. Now, we introduce another straight current-carrying conductor ST of infinite length above XY. This new conductor is in the external magnetic field of the conductor XY such that ST is parallel to XY. Now, we will notice that due to the external magnetic field of the conductor XY, the conductor ST experiences a magnetic force. This implies that there will also be a force on XY due to ST in the accordance with Newton's third law. From this we can understand that two straight parallel current-carrying conductors placed close to each other exert force on each other because they lie in the magnetic fields produced by one another. Now, let us find the force of attraction between the conductors carrying currents in the same direction. Let us first find the force exerted by conductor XY on conductor ST. Let the currents passing through the two straight conductors XY and ST be I1 and I2 respectively. Let the current through both the conductors be in the same direction. Let D be the distance between them. The magnitude of the magnetic field induction is constant at all the points that are at equal distances from the conductor. Let the magnitude of magnetic induction due to current in XY at ST be B1. The direction of the magnetic induction B1 at ST can be found by using the right-hand rule. If we place a stretched right hand such that the thumb indicates the direction of current in XY, the direction of curl of the four fingers of the hand indicates the direction of the magnetic field due to the current in XY, as shown. The magnitude of magnetic induction at any point along conductor ST due to current in conductor XY is B1 is equal to mu naught I1 by 2 pi d. Let us label this as equation 1. The magnitude of the force experienced by a segment of length L of the conductor ST due to the magnetic field produced by the conductor XY is F21 is equal to B1I 2L sine theta, where theta is the angle between the direction of the magnetic field B1 and the current in the conductor ST. Let us label this as equation 2. Here, theta is equal to 90 degrees and sine 90 is equal to 1. Therefore, the force acting on the segment of the conductor ST of length L due to the conductor XY is equal to F21 is equal to B1I 2L. Let us label this as equation 3. On substituting the value of B1 from equation 1 in equation 3, we arrive at the expression F21 is equal to mu naught I1 I2 by 2 pi d into L. Let us label this as equation 4. The direction of the force experienced by the conductor ST due to the magnetic field produced by the conductor XY can be found using Fleming's left-hand rule. According to Fleming's left-hand rule, stretch the three fingers, thumb, four fingers, and central finger of your left hand mutually perpendicular to each other. If the central figure represents the direction of the current and the four fingers represent the direction of the magnetic field, then the direction of the thumb represents the direction of the force acting on the current-carrying conductor. Thus, the force F21 is directed towards the conductor XY. As discussed earlier, the current carrying conductor XY experiences the same force due to magnetic field produced by the current I2 in the conductor ST, which is due to the Newton's third law. The magnitude of the magnetic induction due to the current carrying conductor ST is B2 is equal to mu naught I2 by 2 pi d. Let us label this as equation 5. The direction of the magnetic induction due to current I2 through ST can be found by the right-hand rule. The magnitude of the force acting on the segment conductor XY of length L due to the magnetic field produced by the current through conductor ST is F12 is equal to B2I1L, which is equal to mu naught I1I2 by 2 pi d into L. Let us label this as equation 6. The direction of this force can be found by using Fleming's left-hand rule, and the force acting on the conductor XY is towards the conductor ST. When you compare equations 4 and 6, you realize the two forces F21 and F12 are equal in magnitude but act in opposite directions towards each other. Hence, if the currents of the two parallel straight current carrying conductors are in the same direction, the two conductors attract each other. On the other hand, if the currents of the two straight parallel conducting wires are in opposite directions, then the forces exerted by the conductors on each other are equal in magnitude but repulsive in nature. Thus, they repel each other. Thus, the magnitude of the force F between two parallel conductors of infinite length L separated by distance d, current carrying I1 and I2 respectively in them, is equal to mu naught I1 I2 by 2 pi d into L. Let us label this as equation 7. Therefore, the force acting per unit length of the conductor F is equal to F by L, which is equal to mu naught I1 I2 by 2 pi d. Let us label this as equation 8. Using this expression for force per unit length, let us now define the SI unit ampere. Let the distance of separation between the conductors D be equal to 1 unit, which is 1 meter. Let the current through the two conductors be equal to 1 unit, which is 1 ampere. Then, the force per unit length becomes mu naught by 2 pi. On substituting the value of mu naught, which is 4 pi into 10 power minus 7, we get F equal to 2 into 10 power minus 7 Newton per meter. Thus, if two straight parallel conductors of infinite length, separated by a distance of 1 meter in vacuum, exert a force of 2 into 10 power minus 7 Newton per meter on each other, then the current passing through each conductor is said to be 1 ampere. The SI unit of charge is also defined from the unit of current. If a constant current of 1 ampere passes through the cross-section of a conductor in 1 second, then the charge passing through it is said to be 1 coulomb.